Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is Vapor Absorption Refrigeration System. This is 37th module of the course Thermodynamics and its application. I am Subhashish Maji, professor in School of Engineering and Technology from Indira Gandhi National Open University. Dear learners, let us begin our today's discussion on Vapor Absorption Refrigeration System. After listening to this video lecture, you will be able to understand the concept of Vapor Absorption Refrigeration System. You will be able to explain the performance of Vapor Absorption Refrigeration System. You will be able to solve the numerical related to vapor absorption refrigeration cycle. Refrigeration is the process of maintaining a body or a zone in space at a temperature lower than the local surrounding temperature. Hence, refrigeration requires the continuous transfer of heat from the body or the zone to be refrigerated to the surroundings at a relatively high temperature. It has been explained in our earlier discussion that such a job can be done by a reverse heat engine. However, this is not the only method available for providing refrigeration. There are several other methods used in practice. The most commonly used methods are vapor compression refrigeration system, which we have already discussed in detail in our earlier lecture session. Second one is vapor absorption refrigeration system. Today we are going to discuss on vapor absorption refrigeration system, and there is gas compression refrigeration system and steam jet refrigeration system. Now let us begin our discussion on the topic on vapor absorption refrigeration system. Shown in figure 1 is the schematic of a simple vapor absorption refrigeration system. We call it VARS, vapor absorption refrigeration system. A careful perusal of the figure reveals that the VARS system is essentially the same as the simple vapor compression refrigeration system, except that the compressor in the latter is replaced by the components inside the dotted boundary in the schematic of the former. This is the schematic of vapor absorption refrigeration system. Here you see that there is evaporator. We have already discussed in our earlier lecture session the functions of evaporator. There is expansion device. The function of the expansion device we have already discussed in our lecture session, and there is condenser. You all know the purpose of the condenser, but in this case, that is in the process for vapor absorption refrigeration system, the compressor is replaced by the generator absorber assembly, which is depicted in the picture with the help of the dotted lines. Hence, a vapor absorption refrigeration system can be viewed as a VCRS, that is vapor compression refrigeration system, in which the compressor is replaced by the absorber generator assembly. In the vapor absorption refrigeration system, the work to be supplied for the liquid pump is insignificantly small compared to the work required by the compressor in a VCRS. A distinct advantage of the vapor absorption refrigeration system, but the large amount of heat required to be supplied in the generator leads to poor performance of the vapor absorption refrigeration system. The VARS can hence be used advantageously and economically only in such cases where either waste heat is available as a byproduct or low-grade energy such as solar energy is used for providing cooling. The working of the VARS is explained briefly with the help of the schematic diagram in figure 1. The working substance in the system is a refrigerant absorbent solution. The refrigerant and absorbent selected are such that the refrigerant is a low boiling point liquid and that it has a high affinity to the absorbent. A strong refrigerant absorbent solution, that is rich in the former, is heated in the generator. Let the heat transfer in the generator be Qg. The refrigerant vapor leaving the generator at high pressure is cooled and condensed in the water-cooled condenser. Let Qc be the heat transferred from the refrigerant to the condenser. The liquid refrigerant from the condenser is throttled through the expansion device. Low quality refrigerant vapor entering the evaporator picks up heat QE from it to become saturated vapor and thereby produces the required cooling as in the VCRS. So, the process for VCRS and VARS are almost same. Only difference is in vapor compression refrigeration system we are using compressor, but in vapor absorption refrigeration system the compressor is replaced by the assembly of generator and absorber. The low pressure, low temperature vapor leaving the evaporator enters the water cooled absorber where it meets the weak cool solution from the generator. The pressure difference between the generator and the absorber being maintained by the pressure reducing valve. The generator and the condenser are on the high pressure side of the system while the evaporator and the absorber are on the low pressure side. The refrigerant vapor is absorbed by the weak solution and the resulting strong solution is then pumped to the generator through the liquid to liquid heat exchanger. This heat exchanger is an important component in the system. In the heat exchanger, heat is transferred from the hot but weak solution coming from the generator to the strong solution going to the generator. Thus, the heat exchanger ensures that low temperature weak solution enters the absorber to improve its performance and high temperature strong solution enters the generator to decrease the heat transfer in it, both contributing to the improvement in performance of the system. The COP of the system is given by COP is equal to QE divided by WP plus QG. The COP is low because although WP is very small for a given QE, the QG required is very large. In the simple system explained above, it is assumed that pure refrigerant vapor leaves the refrigerant to be condensed in the condenser. This is barely a fact in practice. The vapor leaving the generator is only rich in the refrigerant component. It also carries a small fraction of absorbent. This absorbent also gets condensed in the condenser, and when it enters the throttle valve, gives rise to several problems in the expansion device and the evaporator. Hence, in actual system, provision must be made to rectify the vapor leaving the generator to assure that only refrigerant vapor leaves the generator and the absorbent vapors are separated, condensed and returned back to the generator. This is accomplished by installing a rectifying equipment, that is analyzer and a rectifier, on the generator. Among the various refrigerant absorbent combinations used in vapor absorption refrigeration system, the most important commercial combination has been the ammonia-water combination, in which ammonia is the refrigerant. A VARS working with this combination is called the aqua ammonia absorption refrigeration system. Another popular combination from the air conditioning point is the water lithium bromide combination, in which water is the refrigerant. Maximum COP of the VARS. If the absorption system were to operate under ideal conditions, then its COP shall be the maximum. To imagine such an ideal situation, all processes must be assumed to be reversible. The system operates continuously in a cycle with 5 interactions. Heat transfer QG to the system at generator temperature, that is TG. Heat transfer QE to the system at evaporator temperature, TE. Heat transfer QC from the system at condenser temperature, TC. Heat transfer QA from the system at absorber temperature, TA. Now let us discuss how we can get the maximum coefficient of performance of the vapor absorption refrigeration system. Work transfer WP to the system at the pump. As the condenser and the absorber are cooled by the water from the surrounding, for ideal conditions TC is equal to TA is equal to T0, the ambient temperature, and the net heat transfer to the surrounding is equal to Q0. So Q0 is equal to QC plus QA. Applying the first law of thermodynamics to the system, so we can write Q0 is equal to QG plus QC plus WP. If the system were to be working reversibly, the net entropy change of the system and surroundings would be zero. There can be no change in entropy of the working substance as it undergoes a thermodynamic cycle. Hence, the net entropy change of the surrounding as well as system must be equal to 0. That is minus QG divided by TG plus minus QE divided by TE plus Q0 divided by T0 is equal to 0. Substituting for Q0 in equation 3 from equation 2 and neglecting WP, which is very small, is equal to minus QG divided by TG plus minus QE divided by TE plus QG plus QE divided by T0 equal to 0. Now, equation 4 can be simplified with simple algebra and rearrange as QE divided by QG is equal to TG minus T0 divided by TG multiplied by TE divided by T0 minus TE. In equation 5, while the term on the left side is the COP of the system, the first term on the right hand side is the Carnot efficiency of a heat engine operating between the generator and the ambient temperature, and the second term is the COP of a Carnot refrigeration system operating between the evaporator and the ambient temperature. Thus, the maximum COP of the absorption system is equal to the product of Carnot efficiency of a heat engine operating between Tg and T0 and the COP of a Carnot refrigerator operating between Te and Tc. In driving the ammonia vapor out of the solution in the generator, it is impossible to avoid evaporating some of the water. This water vapor going to the condenser along with the ammonia vapor after condensation may get frozen to ice and block the expansion device. So, an analyzer rectifier combination shown in figure 2 is used to eliminate water vapor from the ammonia vapor going into the condenser. Now, this is another diagram of vapor absorption refrigeration system. This diagram is exactly same as the diagram which we have explained just now. In this diagram, you can see there is evaporator, there is condenser, there is expansion device, there is generator absorber assembly. Now, in this case, only addition is the analyzer rectifier system. But in this case, what is happening that when the refrigerant leaving the generator, say for the example of aqua ammonia vapor absorption refrigeration system, where ammonia is the refrigerant. Now, when the ammonia is leaving the generator in a vapor state, there may be a chance of some water vapor is also leaving along with ammonia. Now, here the analyzer is there. Analyzer is a open heat exchanger where some trays are there, series of trays are there, alternate trays are there. So, what is happening that in this case the rich solution of the refrigerant is pumped from the absorber to the generator and it falls from the top and passing through the series of trays. Now, in this case, what's happening that if any of water vapor is leaving with the ammonia, that will be condensed and go back to the generator. There is a little chance will be there that some moisture may go with the ammonia and enter into the condenser, but it is then passed through the rectifier. In the rectifier, some cooling coil is there. So if some water vapor is there, that will be condensed with because of the cold water circulating through the coil in the rectifier. So that drip will be sent back to the generator. So ultimately we are getting only ammonia leaving the generator, entering into the condenser. That completes the cycle. So here the analyzer and rectifier, these two are integrated with the diagram of vapor absorption refrigeration system so that it can remove the water vapor which may leave from the generator and enters into the condenser, and if it passes, then if water vapor passes through the condenser and there may be ice formations in the expansion device. So to remove that difficulties or to overcome these difficulties, we must have the arrangement like analyzer rectifier systems should be embedded with the vapor absorption refrigeration system. The analyzer is a direct contact heat exchanger consisting of a series of trays mounted above the generator. The strong solution from the absorber flows downward over the trays to cool the outgoing vapors. Since the saturation temperature of water is higher than that of ammonia at a given pressure, it's the water vapor which condenses first. As the vapor passes upwards through the analyzer, it's cooled and enriched by ammonia and the liquid is heated. Thus, the vapor going to the condenser is lower in temperature and richer in ammonia, and the heat input to the generator is decreased. There is another absorption refrigeration system, namely lithium bromide water vapor absorption systems, as shown in the figure 3. Here the refrigerant is water and the absorbent is the solution of lithium bromide. Since water cannot be cooled below 0 degrees centigrade, it can be used as a refrigerant in air conditioning units. Lithium bromide solution has a strong affinity for water because of its very low water pressure. It absorbs water vapor as fast as it is released in the evaporator. So this is the schematic diagram where lithium bromide and water is used, but the absorbent is lithium bromide and the refrigerant is water. So in this case you see that there is a evaporator, there is expansion device, there is condenser and generator absorber assembly. And in this process, what's happening that when the refrigerant is heated in the generator at a temperature more than 100 degrees centigrade, say at 105 degrees centigrade, the water vapor coming out from the generator and it enters into the condenser, and the heat is giving out from the refrigerant to the outside, that is QC, and that water is passing through the expansion device, and when it passes through the expansion device, its temperature drops down, and that low temperature water vapor mixture is passing through the evaporator and takes the heat from the confined space. After that, it is entering into the absorber, and lithium bromide absorbs water and it will be rich in refrigerant. After that, with the help of a pump, this rich solution sent back to the generator, but before sending to the generator, it passes through the heat exchanger, and hot fluid which is coming from the generator and entering into the absorber, that temperature is high. Here there is a heat transfer from hot fluid to the cold fluid which is going to the generator from the absorber. That's why it is a both way, it is advantageous. The fluid which is entering into the generator is heated, and the weak solution which is coming from the generator, its temperature will be reduced before entering into the absorber. So this is the process for the vapor absorption refrigeration systems, where we use water as a refrigerant and the absorber is lithium bromide. So let us solve a very interesting problem on vapor absorption refrigeration system. What is the maximum COP of an absorption refrigeration system if it has to maintain an evaporator at -3 degrees centigrade while having heat transfer from a high temperature reservoir at 127 degrees centigrade at a place where the ambient temperature is 27 degrees centigrade. Now all these temperatures are given. We have to convert into Kelvin scale. So Tg is equal to 127 plus 273, that is 400 K. So TO is 27 plus 273, that is 300 K, and TE, that is evaporated temperature. Inside the temperature, this is the TE is the temperature inside the evaporator. TE is equal to 270 Kelvin. So we know very well that coefficient of performance for vapor absorption refrigeration system is equal to Tg minus To divided by Tg multiplied by Te divided by To minus Te. So in this case, Tg is given as 400 K, To is given as 300 K, and Te is also given as 270 K. Just put the values in this expression for coefficient of performance, and after calculations you will get the value of coefficient of performance as 2.25. Here we conclude our lecture session. Let us summarize what we have discussed today. We have discussed the concept of vapor absorption refrigeration system. We have discussed the performance of vapor absorption refrigeration system, and we have also solved some numerical related to vapor absorption refrigeration cycle. Thank you very much.